4 astronauts traveled roughly 250,000 miles from Earth, farther than any humans had ever gone, and when they turned their cameras toward the Moon, they captured something extraordinary. These were not distant, grainy images from an unmanned probe. They were detailed photographs taken by human astronauts through the windows of a spacecraft, while traveling through one of the most hostile environments imaginable. Hidden inside those photographs were details that revealed just how different deep space really is. Radiation effects on camera sensors, dramatic lunar geology, an extraordinary eclipse, and landscapes that preserve billions of years of solar system history. But to understand why these images matter, we have to understand how long it took humanity to get back there. After Apollo 17 landed on the Moon in December 1972, humans stopped traveling beyond low Earth orbit. The rockets disappeared, production lines closed, and an entire generation of lunar engineers eventually retired. For decades, the International Space Station became the farthest destination humans regularly reached. At roughly 400 kilometers above Earth, the station is incredibly important, but compared with the Moon, it is practically next door. The Moon is about 384,000 kilometers away. Yet those decades were not simply wasted time. They gave scientists something Apollo could not provide: decades of experience studying how the human body survives in space. Astronauts spent months aboard space stations. Researchers studied muscle loss, bone loss, cardiovascular changes, vision problems, immune system changes, radiation exposure, and the psychological challenges of living away from Earth. NASA also developed increasingly sophisticated life support systems, thermal controls, radiation monitoring, communications, navigation, and spacecraft technology. All of that knowledge eventually became part of the Artemis program. The Space Launch System was designed to send the Orion spacecraft beyond low Earth orbit, while Orion would provide the living space for astronauts traveling toward the Moon. Artemis II was not designed to land astronauts on the lunar surface. It was a crude test flight intended to demonstrate that humans could safely travel around the Moon and return home. The crew included Commander Reed Wiseman, Victor Glover, Christina Koch, and Canadian astronaut Jeremy Hansen. Together, they represented a new generation of lunar explorers. The mission covered more than 1 million kilometers during its journey, taking the crew far beyond the familiar environment of low Earth orbit. And almost immediately, the photographs began telling a story that numbers alone could never explain. From low Earth orbit, Earth dominates the view. From lunar distance, the perspective changes completely. The planet becomes a small, isolated world floating against an enormous black background. Clouds, oceans, continents, and city lights become part of a single object. The astronauts were able to photograph Earth from a perspective that only a very small number of humans have ever experienced. Some images showed the night side of Earth illuminated by a faint glow reflected from the Moon. This phenomenon is sometimes called moonlight or moonshine. That reflected light can reveal atmospheric structures that would otherwise disappear into darkness. The photographs also demonstrated something else: the incredible difficulty of taking professional images in deep space. The astronauts had to manage reflections from the spacecraft windows, control cabin lighting, adjust exposure settings, and carefully frame their subjects while traveling hundreds of thousands of kilometers from Earth. The Moon itself became the main subject. When the spacecraft moved around to the far side, the landscape changed dramatically. The lunar near side contains enormous dark plains known as maria. These regions were formed by ancient volcanic eruptions that filled large impact basins with lava. The far side is much more heavily cratered and rugged. Instead of broad dark plains, astronauts saw overlapping craters, mountains, ridges, valleys, and enormous impact structures. The difference between the two hemispheres is one of the great geological mysteries of the Moon. The far side has a thicker crust on average, which likely influenced how easily ancient impacts could trigger large-scale volcanic flooding. Because much of the far side escaped the extensive lava flooding seen on the near side, enormous impact scars have remained visible for billions of years. That makes the lunar surface something like a geological archive. Every crater is evidence of an impact. Every ridge can preserve information about ancient geological activity. Every layer of material can reveal something about the Moon's violent past. One of the most fascinating regions is the Oriental Basin, an enormous impact structure surrounded by multiple rains. The structure formed after a colossal impact disturbed the lunar crust and produced waves of material that eventually froze into the landscape. Around such giant basins, scientists can study concentric ridges, secondary craters, ejecta deposits, and other features created during the impact. The Moon essentially records its own history directly on its surface. Another dramatic feature appears near the boundary between lunar day and night, known as the terminator. At the terminator, sunlight arrives at an extremely shallow angle. That creates enormous shadows stretching across craters and ridges. Those shadows reveal elevation changes that can be difficult to see under direct overhead illumination. For planetary scientists, low-angle lighting is incredibly valuable because it exposes the three-dimensional structure of the terrain. But the lunar surface was not the only thing revealing the dangers of deep space. The cameras themselves were exposed to cosmic radiation. Beyond Earth's protective magnetic environment, high-energy particles can strike spacecraft electronics and camera sensors. When energetic particles interact with a digital sensor, they can produce bright artifacts that look like stars or flashes of light. Some of these artifacts can appear as isolated white dots in photographs. They are reminders that the spacecraft was traveling through an environment filled with radiation that Earth normally shields us from. Then came one of the most visually spectacular parts of the mission. As Orion traveled around the Moon, its trajectory created an opportunity to observe the Sun being blocked by the lunar disk. From Earth, total solar eclipses usually last only a few minutes. But from a spacecraft moving near the Moon, the geometry can be dramatically different. The apparent movement of the Moon across the Sun can produce a much longer period of obscuration, giving astronauts additional time to photograph the changing illumination. During such an event, the lunar surface can become visible even while the Sun is blocked. That faint illumination comes from Earthshine, sunlight reflected from Earth onto the Moon. At the same time, the solar corona can become visible around the dark lunar disk. The corona is the Sun's extremely hot outer atmosphere, extending millions of kilometers into space. Under normal conditions, the overwhelming brightness of the Sun makes it difficult to observe directly. During an eclipse, however, the lunar disk blocks the bright solar surface and allows the much fainter corona to stand out. The astronauts were able to photograph a scene containing the eclipsed Sun, the Moon's surface, Earthshine, and the surrounding starfield. It is the kind of composition that looks almost artificial when seen in a photograph. Another sequence captured the Earth appearing to move behind the lunar landscape. It can look like a sunrise or sunset on the Moon, but there is an important detail. The Moon is tidally locked to Earth, meaning the same lunar hemisphere generally faces our planet. If you were standing on the lunar surface, Earth would remain in roughly the same position in the sky. The apparent movement in the photographs comes from the spacecraft's motion. Orion was traveling rapidly along its trajectory, changing the astronaut's viewpoint and creating the illusion of Earth moving behind the lunar horizon.